chapter, which is about column damping. Okay, we finished tutorial 5, most of the questions, except the question number 8. Okay, which is about friction. So we will solve this question if we finish this topic. Okay, here we have column damping, which is a result of two surfaces in contact or sliding mode. And this is a dry between two dry surfaces. You will have a friction force which is constant equal to mu times n. You know that for sliding it means it is motion, and then the friction is mu k times n. So, but here k is omitted just for short. But we know this is the kinetic friction coefficient. Mu is the kinetic friction coefficient or coefficient of friction. And N is the normal force. So it depends on how the mass is supported. So what you have usually is a surface, and then you have a mass resting on the surface, and there is a friction here. No, how to move it test. Okay. Okay, this is the surface which is rough, and there is a friction. And then if you add a spring, and this will oscillate. This is not undamped. This is damped, and the damping comes from friction. So the damping means there will be absorption of energy. There will be energy absorption, and then amplitude will reduce with time. If you compare with the viscous damping, and you put the free body diagram in viscous damping, you will have a friction force, spring force Kx, and a damper force Cx dot, right? And the mass. And here the free body diagram will be a spring force Kx. The friction force, because it is a constant, it is not multiplied by velocity. So for the viscous damping, that the direction of the damper force will change if the velocity change sign. Okay, so that the positive direction is to the right, that is positive, and positive of x and x dot. And if the velocity is negative, then the direction of the force will change automatically. That is because it is multiplied by velocity. But if here we don't have the friction force is not multiplied by velocity. We know it is always in opposite direction of the velocity of motion. So here it depends where is the type of motion or the direction of motion in order to put the direction of the force. So we have to adjust the direction of the force manually. And you know that in oscillations, it means cyclic, and it will move right to left and left to right. So at E, and this is in one cycle. In one cycle, the mass will go in one direction to the right, say, and then it will move to the left, and this will complete one cycle. Okay, so it means that the free body diagram we should have here should be for each half cycle. Okay, the free body diagram here is for all cycles for the viscous damper, for all cycles, because the spring force will change direction because of the sign of x. The damper force will change direction because of the change of sign of the x dot. But here the velocity is not multiplied by the friction force because the friction force is simply a constant equal to mu times n. So we have to change this manually. and this makes some complications. Okay, so we have, it depends on the type of motion or direction of motion. Let's say direction is from motion from, or the mass is moving from left to right. Okay, it's moving in this direction. So the friction force will be in this direction. This is Fd. And then the free, this is the free body diagram. And then you will use sum of forces equal to mx double dot. To the right is positive. So we have minus kx minus friction force equal to mx double dot. And then we rearrange. F is a constant, so we can keep it on one side. And this will be mx double dot plus kx equal to f. F is equal to mu n, constant. Okay, for the second half cycle, this is first half cycle. In the second half cycle, when the mass is moving from right to left. Okay, the free body diagram becomes kx will be the same because the free body diagram is drawn when the mass is on the positive direction. But at the positive direction, okay, let's say this is the positive direction, and the mass is here, and this is the spring. Okay, if it is moving motion in this direction, and you can have the same free body diagram, but when the mass is moving in this direction. So you draw the free body diagram at the same position, but the mass motion is either to the right or to the left, so that the spring force is always to the left. Okay, the spring force in the both the free body diagrams, that kx is always to the left. The friction force here will be to the right because the motion is from right to left. And sum of forces equal to mx double dot, we will get minus kx plus f. Here there is a minus sign. Okay, equal to mx double dot. Okay, we take minus kx to the other side, we get mx double dot plus kx equal to f. So we have two differential equations which are not the same for one cycle. This is half cycle, and each differential equation is valid for a half cycle. And imagine you will do this for all cycles. So let's say this is the first cycle. It is divided into first half, second half. The second cycle also will be divided into first half, second half, and so on, until the motion will stop. Now, we cannot continue this way because we will face a problem that when it is going to stop. But this will give us an idea about the differential equation, the left-hand side in both of the equations, equation number 1 and number 2, that the left-hand side of the differential equation are the same in both equations, mx double dot plus kx, mx double dot plus kx. The left-hand side, the right-hand side, for equation 1, it is minus f, which is a constant, and f for the second equation, which is just a constant. And when you put the solution, this is similar. The left-hand side is similar to the n-dam system. There is no c times x dot here. So this is the left-hand side, same as the n-dam. The solution of those equations consists of two parts. The homogeneous part when the equation equal to 0, and a particular. A particular because we have a constant. We have the right hand side is not 0. So the solution should be two solutions, homogeneous plus particular. The homogeneous, it means when it is equal to 0, and this is what we did for Andam system. And the particular solution is a solution that satisfies both sides of the equation. That we cannot assume any solution here for the particular. For the homogeneous, is going to be, okay, so the solution will be, it consists of two parts, x homogeneous plus x particular. Homogeneous is same as unbound. Unbound system, which is x h equal to a cosine, we use a sine omega nt, plus b cosine omega n t. Okay, you can go back to the beginning of the chapter of Andam system. You will see that this is a solution, but we don't substitute for a and b here. Okay, a and b are to be found from the total solution, not from just the homogeneous. The particular should equal to a constant c, because the right hand side is constant. So for a solution of equation number 1, will be x equal to a sine omega nt plus b cosine omega nt, and there is a minus, so this will be minus, and the value of c, when you substitute in the differential equation, mx double dot is 0, because c xp is constant, so x double dot is 0, so it's going to be k times c, and c becomes minus f over k. So this will be minus f over k. This is the particular solution. And solution of equation number 2, x will be, let's say, c d sine omega nt plus e cosine omega nt plus f over k, because we have f, positive f. The two equations, if this is those two equations are for the first cycle, then we should have associated with the differential equation should be the initial conditions. Okay, initial condition for, if this is the first cycle, it means initial condition at t equal to 0. It should be given x at 0 and x dot at 0. For the second equation, you cannot proceed if you don't know what are the initial conditions. Initial conditions for the second half cycle are x at not at 0 here, that should be obtained from the previous solution. Okay, is or are obtained at the end of the first half cycle. Yeah. Okay, I have to restart my computer. Yeah, one note will not work, and even if I close and come back, it will not work. Just hold on a second and see. Okay, I will come back. Okay, I will come back. Huh? اوكي. لازم حضور، لا الامتحانات كلها حضور. Okay, so we are. I'm back now after I restart my computer. Okay, so we talked about. ما شغلت لكم هنا بعد. Okay. Just 1 second. اشتغل؟ Okay, so we were talking about the solution of equation number 1 and equation number 2. And those two differential equations are the equations of motion for the first half cycle and the second half cycle. For each differential equation, we need initial conditions. For the first half cycle will be the initial condition at t equal to 0. The second half cycle, the second equation, the initial conditions will be obtained from the end of the first half cycle. From the solution of the first half cycle. Okay, so I'm not going to go through the solution now, the final solution, because those two equations are for one cycle only. So you can use this from 0 to tau over 2, and this is the second equation from tau over 2 to tau. This will be one solution. Usually the solution, if you want the response, the solution is the response, which means x with time. Usually for this, you need to use numerical method. Okay, because there is a function in MATLAB, or even you can code this in the procedures of solving differential equation, that the force is multiplied by the sign of the velocity, not the velocity, multiplied by the sign of the velocity, so that the force will change directions. So what you do is you multiply F, which is equal to mu times n, you multiply it by sine of x dot. Sine of x dot is a function you can create it yourself as well. Is equal to x dot divided by a magnitude of x dot. So this way it is 1. It is either -1 or 1. And this will give you that the sign of the friction force, and it will change automatically. But this can be done by a numerical method without specifying half cycle, second half cycle, first half cycle, and so on. And you can solve it numerically. You get the answer. Okay, but now, so why I did this? I did this for a reason, to show you that the frequency of oscillation, as we mentioned in the viscous damping, that the frequency of oscillation will be either omega d for underdamped or 0, right? For overdamped or critically damped, because they have no oscillations for overdamped and critically damped. So here it is friction damped or column damping, and the frequency of oscillation will be omega n, because the frequency of oscillation, or we look at the argument of sine and cosine in all the solutions. And if you proceed to the second cycle, those terms will not change. Yani sine omega n t, cosine omega n t will again appear, plus a constant. So it means that the frequency of oscillation, as an observation, that frequency of oscillation of column damping is omega d equal to omega n. There is no change in the frequency of undamped. Undamped is natural frequency of undamped system is omega n. Then the frequency of oscillation or natural frequency of damped oscillation in column damping is omega d, is omega n. Omega d equal to omega n. There is no change with the undamped system. So that is one of the conclusion I wanted to reach to. So if you have a friction involved only, not viscous damping, only friction, you know that the frequency of oscillation is unchanged, that is equal to omega n. And the procedure I did is only to show you this conclusion. But the actual solution or the response, if you want to seek that, for all oscillations, I prefer that you do the numerical method. Okay, what else we can do is to find, this is the regarding the frequency and of course period of oscillation, omega n or omega d is omega n and tau d is tau n. Okay, so what else we need to find is the relationship between the successive amplitudes, as we did with viscous damper system, that the ratio in the viscous damping system, the ratio of any two amplitude of consecutive cycles is constant, the ratio. So we need to find the relationship between successive amplitudes here as well. So instead of looking at the solution or the response, we can relate the amplitude of successive cycles. Okay, we can do that by using what we did in dynamics, which is called work and energy, principle of work and energy, if you remember, that we can use T plus U from 1 to 2 equal to T2, T1, the principle of work and energy. We take 2 points, and this is energy method is applied that relate 2 points at different instant of time. So if the mass is, I will take, this is the equilibrium position when the mass is here. This is at 0 position. This is the equilibrium. Now, if you move the mass to the extreme right, so the spring will be stretched to this point. This is one, left, right extreme at the end. And we will call this as X1. Okay. And the motion will start from right to left. And we'll go back, we'll pass the equilibrium and go to the left side. And this is the extreme left. And we will call this position as X of -1, extreme left. And then it will go back to the right and will reach again extreme right with position X2. And then we'll go back to the left and we'll reach a position extreme X -2, right? X -2. This is X2 and this is X of -2. And then we'll go back to X3 and so on. And then X of -3 and so on. As you can see from this graph, this is the extreme position at position 1. And then this is the extreme left, which is X of -1. And then this is the extreme right, which is X2. This is one cycle here. Okay, and we want to relate X1 and X2. The principle of work and energy, we cannot apply it from 1 to 2 directly from extreme right to the extreme right because of the friction is a non-conservative force. So we can only do it in one direction, okay? Which means it goes from, let's say, from position 1 to position 2. This is in one direction. Okay, I don't know how to show this. This is the surface. This is position 1. And this is position 2. And here is the equilibrium. The position is x1, and the position here is x of minus 1. Okay, this is from motion from right to left. Okay, and then you can apply the principle of work and energy, that is T1 plus U from 1 to 2 equal to T2. What do we have at extreme position? What are the velocities here? 0. Yeah, because at maximum position we reach the momentarily the velocity, or it is stop. It will stop momentarily. So the kinetic energies both are 0. Then we have only the work done. Okay, so based on your knowledge from dynamics, we have two forces here: the spring force and the friction force. The work of the spring is 1 over 2 K x1 squared minus x of minus 1 squared. Okay, and it is, if you want, this will be x2 squared, but x2 is x of minus 1. Yes, we name it x of minus 1. Always the friction force is negative. It is F times the total distance d. D is x of 1 plus x of minus 1. Now x of minus 1 is absolute value here. Just think of this as absolute value. X of minus 1 is the positive value. We are taking distance. We are not taking, okay, so let's say this is d equal to 0, and d is this distance. So it is simply equal to x1 plus x of minus 1 equal to 0. This we can factorize the first bracket. So this would be 1 over 2 k x of 1 minus x of minus 1 multiplied by x of 1 plus x of minus 1, right? We can do this. Minus f times x of 1 plus x of minus 1 equal to 0. And as you can see that this bracket will cancel out. And then you can have that 1 over 2 k x of 1 minus x of minus 1 minus f equal to 0. And we can put x of 1 minus x of minus 1 equal to 2f over k. Okay, now we move to the second half cycle, which is from point 2 to point 3. From point 2 to point 3, we apply the same principle. Okay, the principle, it means here is position 2, and this is the equilibrium position, and this will move to x2. So here it is x of minus 1, and here it is x of 2, and the motion is in this direction. Again, we apply the principle of work and energy. And again, that the kinetic energies are both 0 because those are extreme positions. Then we have only u from 2 to 3 is equal to 0. The work again is for the spring and the friction force. The spring is 1 over 2 k x of minus 1 squared minus x of 2 squared minus f times d, and d here is x of minus 1 plus x2 equal to 0. And we can expand this again. We are doing, similarly. You can expand this. And this will be x of -1 plus x of 2 minus f times x of -1 plus x of 2 equal to 0, which is this bracket will cancel out. And then you can put x of -1 minus x2 on one side. This becomes 2f over k. Okay, this is equation number 1, and this is equation number 2. If we add them together, we'll cancel x of -1. And then we get x1 minus x2 equal to 2f over k plus 2f over k is 4f over k. This is the final equation that relates to consecutive amplitudes. X1 is the amplitude of cycle number 1. X2 is the amplitude of cycle number 2. And if you substitute for f, this is 4 mu n over k. N is the normal force. Okay, m is the normal force, and obtained from sum of y. Equal to 0. So if you have a horizontal surface, we draw the free body diagram. This is the normal force. This is mg. And when you have kx and you have a friction force either this way or this way, so sum of fy equal to 0, which will give us that n equal to mg. If you have inclined surface at an angle theta, yes, then the normal force, this is the y direction, this is the x direction. Then again, sum of fy equal to 0. This means that when you put the weight here, this is theta, and here is the normal force, and you have the spring force kx either this way or this way, and this is the friction force. Then it is n equal to mg, or the weight. Okay, cosine theta. So either this or this. Okay, so what you can see from the observation again, from what we did using the principle of work and energy, that x1 minus x2 equal to 4 mu n over k equal to constant. So if you choose to do this with second cycle, which means x2 to x3, the difference will be the same. So x3, okay, this implies that x3 minus, x2 minus x3 is the same, is equal to 4 mu n over k, or and even the x3 minus x4 is the same. So that means the characteristics of column damping, it means that one thing is that the frequency of oscillation is unchanged, equal to omega n, and that the difference between consecutive amplitude is constant. So as a comparison with viscous damping, the frequency depends on zeta, which can be either omega d equal to omega n square root of 1 minus zeta square for zeta less than 1, or equal to 0 for the others. Okay, and that the ratio for underdamped case, a ratio is constant of amplitude. Here the difference is constant. So those are the characteristics. They are summarized here in last page. It can be shown that the frequency of oscillation is omega n square root of k, which I showed you. That which is undamped natural frequency, that omega d equal to omega n. The amplitude decay linearly because of the difference. The amplitude will decay linearly, as you can see here. The peaks, okay, the peaks are on a straight line. They lie on a straight line. Even the other peaks, they lie on the straight line. And this is called decaying linearly. in viscous damping, the decay was exponentially decaying. Exponentially decaying. This is linearly decaying. And the amplitude of any two consecutive cycles is given by x of m minus 1 minus xm equal to 4 if d over k, if d is friction force. Okay, equal to 4 mu n over k, m equal 1, 2, and so on, which is the cycle number. So for the first cycle, you will have x0 minus x1. In the second cycle is x1 minus x2, and so on. Okay, and this is the end of the chapter. We go back to the tutorial. There is one more question. A mass of 20 kilogram slide back and forth on a dry surface due to action of a spring having a stiffness of 10 Newton per millimeter. After 4 complete cycles, the amplitude has been found to be 100 millimeter. What is the average coefficient of friction between the two surfaces if the original amplitude was 150 millimeter? How much time has elapsed during the 4 cycles? We have the mass is equal to 20 kilogram. We have K equal to 10 Newton per millimeter. So we can find omega n equal to square root of K over n. We have to convert the units. This will be 10 times 10 to the power 3 divided by 20. After 4 complete cycles, we have that the equation is xm minus xm, xm minus 1 minus xm equal to 4 mu n over k. So we have for the first cycle, this is x0 minus x1 equal to 4 mu n over k. And x1 minus x2, this is the second cycle, is 4 mu n over k. And then x2 minus x3 equal to 4 mu n over k. And the last one is number 4, x3 minus x4 equal to 4 mu n over k. The relationship, the difference between two the amplitudes, the difference between two amplitudes of 2 consecutive cycles. Okay, so we have the equation we reached to in the last slide here is that xn minus 1 is the amplitude of any 2 consecutive cycles. The difference is constant equal to 4 mu n over k. Now in the question we have 4 complete cycles. It says the amplitude has been found to be 100 millimeter after 4 complete cycles. 4 complete cycles after 4 complete cycles. This is the beginning of cycle number 5. Okay, so we have if you just sketch the cycles. Okay, from here to here is 1, then this is 2, okay, then 3, then 4. So we have x0, x1, x2, x3, x4. The amplitude of x4 is given, and amplitude of x0 is given. So so we add them together. We get x0 minus x4 equal to 4 times 4 mu n over k. So you can generate a general equation that x m minus 1 minus, and let's say x0 minus xn equal to n times 4 mu n over k, which x0 and xn are separated by n cycles. Okay, then we can substitute x0 is 150 millimeter. في الكتابة ساعات الشيء. Times 10 to the power minus 3 minus xn, which is x4, is 100 times 10 to the power minus 3 equal to 4 times 4 times mu, which is unknown, times n. N here is, we have to use sum of Fy equal to 0 and that n equal to mg here. So this will be m, which is 20. 20, right, times 9.81 times mu divided by k, which is 10 times 10 to the power minus 3. Plus 3, not minus. This is multiplication. Okay, you can find the mu from here. Okay, the second part of the question is, how much time has elapsed during the 4 cycles? What shall we do here? We go back to the definition of omega n or omega d, because this is damn the free vibration, but Coulomb damping, and that the frequency of oscillation is unchanged. So it means that omega d equal to omega n, right? So we can find the solution here. And then for the second part, we have omega d equal to omega n equal to 2 pi over tau n. So the tau n is the time for 1 cycle. The question, we multiply this by 4 because the question is to find the time for the 4 cycles. So t for 4 cycles is 4 times tau n. Okay, tau n is equal to 2 pi over omega n, equal to 4 times 2 pi square root of m over k. That's it. And you can substitute here. Okay, so this is the end of chapter 2. Hey, the same. Okay, this is tau is the same for all cycles, period of oscillation for a free vibration. Okay, any questions? Okay, so we'll see you inshallah on Tuesday, right? Which is the test. But we'll see if you have any questions for the test, we can meet during the lecture time. Okay, awesome.